Now we're ready to take a big leap forward in terms of the practicality of our methods. See, when we've been doing these integrals, okay, we have these trapezoidal forms, right, which we can do, and then we can take two trapezoidal evaluations and turn them into a Simpson, and then we can take two Simpson evaluations and turn them into something which is even more accurate, sixth order. But all of these things are based on an equally spaced node situation. So the H determines the size of the grid, and that's fine in many cases, but sometimes you might have a function that does something like this, where it varies very slowly, and then it varies rapidly, and then it varies slowly again, right? So obviously you're going to want a lot more points in here to figure out the function in the middle than you will to figure out what's going on near the ends, where it's varying quite slowly. It doesn't take a lot of points. So we want to be able to adapt the nodes to the integrand. So even though we have a method that works perfectly well on all problems, we also want methods that adapt themselves to the problem at hand so that they can get things done more efficiently. Because if the function is slow to evaluate, then we want to minimize the number of times we do it. Okay, so here's how it goes. Right, we have a second order estimate. We turn two of those into a fourth order. We turn two of those into a sixth order. So what we'll do is we'll use, we want to use an S value as the integral, and then use R minus S to estimate the error. Okay? So R should be a better estimate than S itself, so it should give us a good idea of how accurate S is. So here's how it goes. We start on the full interval AB with first one interval, then two intervals, then four intervals for the integration. So what that means is, right, for n equals 1, we have just these 2 points. For n equals 2, we have 3 nodes. And for n equals 4, we have 5 nodes. Okay, so we get a t here. So I'm going to switch to using n instead of h here. So t1, t2, and t4, let's say. All right, only 5 different evaluations of f, because the one case shares 2 of its nodes with the 2 case, and the 2 case shares all 3 of its nodes with the 4 case. So there are only 5 evaluations needed. Okay, so we use those to generate S values, and then we use those to generate an R value. Okay, let E be the difference between the R and the S. All right, if that's small enough, then we stop. We return S1. If not, okay, what we're going to do is we're just going to divide the integral. So we let m be 1/2 a plus b, so the midpoint. And then I is just the integral from a to m plus the integral from m to b. So computer scientists know this as divide and conquer, right? You take a problem of the full size, you split it into 2 or maybe more problems of smaller size, and then you glue the results back together. Well, in this case, the gluing is really, really simple because the integral on the whole interval is just the integral on each piece added up. So we do this and this separately, and we recurse. right? So in other words, we recursively try to do this integral and that integral. So it really is quite simple. There are two details that are important to know. So one is, what does small enough mean? Okay, so as always, we have to be concerned with relative errors as well as the absolute errors. If you're trying to compute the integral for a very, very large quantity, you can't expect to get a whole lot of decimal places. We can only ever expect to get maybe 15 or 16 digits. So that means that what we usually do is we create two error tolerances, call them delta abs and delta relative, and then we say it's okay if we can write that E is less than delta absolute error plus the relative error times the actual value that we're trying to compute. All right, so that way, if this number is really big, okay, this is the part that we have to worry about. If, on the other hand, the value we're trying to get is not very big, it's quite small, if you have an integral of a cosine function and it's almost supposed to be 0, right, because of the limits that you chose, well, we can't get high relative precision in that result because some of the values of the function are about 1, so we could never get 10 to the minus 30, for example. So then this is the condition that would kick in. We would just stop if the error got small enough in an absolute sense. So this works whether or not the result is large or small. Second detail is to be frugal with our F evaluations. So let's say we've done our calculations. We did our 3 trapezoid rule approximations and found out that we need to subdivide and recurse. So this point here is the point M. So now we're going to split this into two integrals, one of them from A to M, and another one which is done completely independently from M to B. So two recursive calls. Well, for one thing, right, it would be silly for us to reevaluate f of a every time at every level, right? We just want to keep using that value. Same for f of b. We just want to keep reusing that. Same for f of m. That gets reused twice. And not only that, but this point here is the new m in this interval. And this point here is the new m, the new midpoint in this interval. So really, all of these 5 evaluations we did up here can be recycled and used at the next level down. And the only thing that we're going to need to do at those new levels is to evaluate at these points that I never used before. And so this is all very simple to see and describe. It just takes some effort to do the calls. You have to do some bookkeeping in your function calls in order to make sure that basically that 3 function values get passed down in each recursive call. With that, you get a very effective method for a wide range of different kinds of integrands.